Hey, welcome back to our Boondocking 101 series, a series where we're talking about all the basics of boondocking. My name is Chris, I'm with the Flying Hens. Thanks for joining us today. In this video, we're going to talk about the electrical components and how that kind of ties into dry camping. So we're going to discuss generators, solar panels, and the systems that go along with that. All the different components of that system. We're going to talk about boondocking tips on how to conserve electricity when you're out in the middle of nowhere. We're going to discuss a little bit about like what electricity and electrical systems and everything consist of, like AC and DC, and you know, the different terms and some of the formulas that go along with that. Now, take that for just a layman's advice. I'm not an electrician. I'm not an electrical engineer. You'll probably notice that in this video, but I'm here to just help, hopefully, increase your knowledge just a little bit more. But finally, we're going to discuss how do you right-size a solar system to your RV? Like, what are your needs, and what is the goal for designing a photovoltaic system for your RV. And that'll be at the end of the video, where we'll sit down with a full worksheet to design a system. Otherwise, let's just move on to the boondocking tips. Well, let's talk about conservation. That's the number one rule of boondocking in general, whether it's water or waste or electrical or anything in boondocking, trash. Electrical conservation. Pretty simple. I mean, number one rule is turn it off if you're not using it. Save as much power as possible. Also, some of your appliances, like your refrigerator and your water heater, will run off of propane. It's easier to refill a propane bottle in a lot of places than it is to create solar electricity when you have no sun, or your generator, you're going to have to go refill gas on that anyways at some point in time. So propane typically will last longer and prolong your time out in the middle of nowhere. The other thing to remember is, like, when you're using that propane water heater, you don't need hot water all the time. You may need hot water just to take a quick shower. So leave it off so you conserve your propane or your electrical. If you just have an electrical water heater, you conserve your battery power by just turning it on 5-10 minutes before you need to take that shower. Do a nice quick shower, turn it off, and save as much as possible. Other ways to save: parasitic draw. Remove it, get rid of it. So when you have a phone charger plugged into the wall, even if your phone's not plugged into it, it's going to be drawing just the slightest little bit of power while plugged in. So unplug the empty charger. The same concept can go for any electrical item in your RV. Even like appliances. You can go kill the circuit breaker on each individual circuit in your RV to prevent unnecessary, parasitic draw throughout the RV. The other things to think about, like when you're in the summertime, like park in the shade, park in the trees, so you don't have to run your air conditioner as much. In the wintertime, you can try to find an open field to park and utilize the sun, the radiant heating, the exact opposite effect. Try to utilize opening windows and doors to create drafts instead of needing the AC. The foil insulation that you can put in your windows to help prevent the heat loss or the heating up of your RV in the summertime. That all helps in reducing what you need electrically when it comes to specifically your air conditioner. All these ways are ways to kind of help reduce your electrical needs when you're out there. So when you're boondocking, you don't have shore power. So you have to have electrical power from something to recharge your batteries and run the AC equipment that's on your RV. You have a generator and you have solar. Okay, so generators, you have two types. Some are actually built into the RV. They come from the factory that way. Our toy hauler has a 5,500 watt Onin gasoline generator. Or you can get portable generators that you can take anywhere. You just crank them up and they run and supply power anywhere. The portable ones, they can come from 1,800 watts all the way up to 8,000-9,000 watts if you really are wanting to get that large. For an RV application, 3,500 watts is great. If you want to get away with just a backup generator, you can do like a little 1,800 watt generator as well. That's what we have as backup to our solar, just in case. The pros to generators, they're inexpensive. They also can have a large output potential. So you know how I was saying that you could do a 3,500 watt. If you really wanted to, you can get a 5,500 watt portable generator, recharge your battery bank in just an hour or two. The other thing is it's power when you need it. So if it's nighttime, if it's cloudy, if you have all these other little restrictions that solar kind of gives you, you can still get power with the generator. There's also multiple fuel sources. So if you run out of gas, which you always have to have gas to run your generator, you can use propane on some generators. It's not as efficient, but it's a great power source that you always have available. And it also allows you to park anywhere you want. You're not restricted by trees with shade or leaves or anything like that. Cloudy days, like if you're in the Pacific Northwest, it's not going to be an issue when you have a generator. So you have a lot more versatility with where you can go at any time. Cons, they're noisy, okay? Imagine you pull up to a nice serene boondocking spot, you get yourself all set and ready to go, but then you got to kick on your generator and all you hear is the whole time. It's not ideal, but it's not a bad place to start. You have to think about the exhaust fumes. The exhaust fumes of your generator are going to have carbon monoxide. It's a poisonous gas, and you won't even know it's there unless your carbon monoxide detector goes off like it has on us. We've put our generator down below here, and when we kick on the generator, with a little bit of light wind from this direction, it was blowing the exhaust into the RV. We didn't know about it until we were woken up at about 2 o'clock in the morning by the carbon monoxide detector going off. So always be aware of where the exhaust fumes are going and venting. Try to keep them far away from your RV. You also have to keep gas with you at all times because it doesn't run without gasoline. So extra gas cans, just more things that you have to kind of store with you. You also have to store it somewhere. So it takes up space in basement storage or in the truck bed, along with the gasoline that has to go with it. So that's kind of a couple cons to the storage aspect. There's maintenance and setup. All right, so you've got to maintain it. Oil changes, filter changes, making sure that the carburetor's clean and you can't let the gas sit in there for a long time. The setup. Everywhere you go, you got to set it up. You got to turn it on every time you need power. You've always got to be thinking about, okay, power, generator, gasoline to keep yourself going with power. Last but not least, the output is affected by altitude. So something you don't necessarily think about when you go out there, it's, if you're boondocking in Florida, not a big deal. But when you go up into the Rockies or you get out into the high desert and you're at 5,000-6,000 feet, generator output goes down about 10% for every 3,000 feet of altitude. So if you've got that 1,800 watt generator, you go out to the high desert, it's probably not going to run your 1,500 watt air conditioner, especially with the startup peak wattage of the AC. So that's going to be an issue to think about. Make sure that you size your generator appropriately. Things to think about when you run your generator though, a lot of places have quiet hours. And even if you don't have a place that has quiet hours, please respect nighttime use of your generator. If you can get away with not running your generator at nighttime, please do so. So what a lot of people will do is they'll run their generator in the morning for an hour or two to recharge what they used overnight. And then they'll charge their battery right before bed for a couple hours and make sure that their generator stays off from 9 o'clock, 10 o'clock at night until the morning time. So it's one way that you can use your generator and be courteous to your neighbors around you boondocking. As far as solar goes, okay? Solar, nice pros to it, it's silent. There's no noise in the generation of solar power. There's also no maintenance except for making sure your panels are clean and clear. As you can see right now, mine are pretty clean, but you can see the leaves all around me. Those leaves were on my solar panels at one point, and it was reducing my my output. However, I'm in an RV park because we don't always boondock, so that wasn't a big deal because we're connected up to the pole. There's also no setup required if they're roof mounted. You don't have to store them anywhere. They're all right here. Some of the portable ones, you do have to set up, kind of angle them towards the sun, and that's about it. But you just leave them there the whole time. The lifespan of solar panels, it's about 25 years, okay? You're gonna get 20 to 25 years out of the panel, which is probably longer than you're gonna have your RV. So that's a great perk to solar, is once you install them on your roof, you most likely never have to replace them. Problem with solar though, it's expensive. Not necessarily the panels themselves, but the initial cost of all the other components that go with the panels to create your overall system. You also need direct sunlight, okay? So it's reduced by indirect sun that you're gonna get during the wintertime because the sun is lower in the sky. If you go further north, once again, the higher latitudes, you have lower sun angle, and all that's gonna reduce your output, along with shade and clouds and the obvious things that reduce sunlight and the time of day. So you're only gonna get about 5 hours of good sunlight, like for peak solar charging. That's gonna be when the sun kind of comes up. Gonna have it about 10:30, 11 o'clock in the morning till about 3 or 4 in the afternoon, and then it starts going down low enough on the horizon to really reduce your output. And last but not least, you're limited by the amount of real estate you have on your roof. I've got a 43-foot RV, so I'm not really worried about that as much as somebody who might have a small 20-foot travel trailer. You have limited space. So you have more energy potential out of a generator than solar panels in that case. But 43-foot RV, I have 3,000 watts of power, and I could even go up to 4,000 if I wanted to. Why would you go generator versus solar? Well, you're gonna look at the versatility of what you can do with each item, your budget, and then the convenience factor. So the versatility, a generator is gonna let you go to more places because you don't have to worry about, am I gonna have sun if I go in this forest for boondocking? But you also just have the noise factor that goes with that. Do I really want to have that noise? Budget. Can you afford to put a whole photovoltaic system in, or do you have to start small, work your way up, or just start with a generator? If you're new to boondocking, you may just want to start with a $500 generator and be good with it. Also, the convenience factor. That's where solar really takes the cake. I mean, the convenience is it's always doing its job as long as there's sun. There's no setup. I don't have to worry about, okay, do I have to go turn on the system? No, I don't. It's ready to go. A couple questions that I get regarding solar is, can I run my air conditioner off solar? Well, that's not really how it works. So to run an air conditioner, you need alternating current power, which is going to come from an inverter off of your battery bank. So really the question is your inverter strong enough? So do you have a 2,000 watt or more inverter to run an air conditioner? And do you have enough battery bank to run it? Because the solar panels only just recharge the batteries. So if you've got enough solar to recharge the battery at the current draw of the air conditioner, then yes, you can do that, given the fact that you have a good enough inverter for it. The other question I get is, how much solar do I need for my RV? But that's gonna be something that we need to calculate later, and we're gonna do that in this video in the second half. And I've got worksheets to really kind of work all that out and make sure you get the right setup for your RV. Let's talk about the electrical terms and calculations that we're going to use. Voltage is the force that drives electricity through a resistor or a conductor. The higher the voltage, the easier it is, and the more current that can be pushed through a given conductor or resistor. Current is the flow of electrons through a conductor. It's measured in amps or amperes. And that is the measurement of the current flow, and it's an indication of how intense the electrical charge of a system is. Power is the rate that the electricity is being transferred through a system, and it's measured in watts. It's the amount of work that's being done at any given moment. Watts is the measurement of the rate of electrical transfer, similarly to the speed of water in a river going 5 miles an hour. This doesn't mean that it has gone 5 miles, it's just the current flow rate at any given time. Watt hours is the measurement of energy being used or the capacity of like a battery. It is not dependent upon the voltage of the system or battery. Amp hours is the measurement of capacity and or electrical usage, kind of like a watt hour, but it is relative to the voltage of the system. Ohm's law is the basis of all electrical calculations, and it states that the force required to move electrons through a conductor is equal to the current times the resistance. For our purposes of the calculations we're going to do, it doesn't really apply to a lot of the things for building an RV solar system. However, it is very important to understand. Watt's law, or the electrical power formula, states that if you multiply the current times the voltage, you get the power, or watts. This is important because when we're designing a system, we are going to use this formula to calculate the watts and the subsequent watt hours of each device. If you have a coffee maker, let's say, that plugs into 120 volts and pulls 10 amps, then it's a 1,200 watt appliance. If the heating element is used for 5 minutes a day, the coffee maker will use 100 watt hours of battery capacity a day. Convert that to a 12 volt system and it'll consume 8.3 amp hours of battery capacity a day. Let's take two standard 12 volt batteries. They have 100 amp hours each, and we're going to first wire them up in series. Okay, wiring in series means that you're connecting positive to negative, positive to negative, positive to negative throughout the entire battery bank that you have, whether you've got 2 batteries or 4 batteries or 7 batteries. When you connect in series, the voltage becomes additive. So you add all the volts of the batteries together, and the amp hours, or the capacity, remains the same. So the total system voltage is now 24 volts of these 2 batteries, but the amp hours remains the same at 100 amp hours. So to find out the watt hours of power, you take 24 volts times 100 amp hours and you get 2400 watt hours. So let's go back to our 2 batteries and wire them together in parallel. That means that we're going to wire the positive terminals to the other positive terminals and the negative terminals to the negative terminals. And then when you wire in parallel, the voltage remains the same and the amp hours are additive, and therefore we now have 200 amp hours at 12 volts. In order to get the watt hours of this total system, you do 12 volts now times 200 amp hours, and once again we get 2400 watt hours. So you can see that watt hours, the overall electrical capacity, does not change. So the advantage of wiring in series is you can increase your overall system's voltage. When you increase the voltage, in order to put out a certain amount of power, you need less amperage or current. So when you have lower current draws, you can use smaller gauge wiring. You don't need heavy gauge wiring when you're working in higher voltage. Now, the disadvantage is your capacity doesn't really increase as far as the total run time. So if you're running a 24 volt system, you still only have 100 amp hours of battery life. When you're running in parallel, the advantage is you've increased your run time, but you have the lower voltage, which means that you have higher current draws with the higher powered items. Therefore you need thicker, heavier gauge, and therefore heavier in general wiring in your RV. Let's talk about the components of a photovoltaic system. Let's start with solar panels. That's going to be your main component. Boom. Most of them are silicone-based solar panels. And so the photons of the sun come down, hit the silicone, and it pushes electrons through the panel. That creates the electricity. Now, the silicone itself, there's monocrystalline and there's polycrystalline. That's just the way that the crystals inside the panel are created. One is more efficient, the monocrystalline. Okay, for the given size of the solar panel, it's going to create more power than a polycrystalline solar panel. However, it also costs more than a polycrystalline solar panel. So when you look at that, it's like, which one do I get? Well, polycrystalline's more budget friendly. If you've got the real estate like I do, then go with a polycrystalline, and which is what I did. These are 250 watt panels, and you'll be just fine. The monocrystalline panel, same size, you could probably get upwards of 350, close to 400 watt panels for the same real estate. Lastly, there are flexible, thin film solar panels. Those are actually, they either kind of roll up or they will flex, they might fold up. Those are not silicone based, but they operate the same way. They push electrons through the panel, and they're easily storable. So if you don't have the roof space for it, but you can roll one up and shove it in your basement storage or keep it in your truck, that might be the way to go. A couple numbers you need to know about solar panels are the VOC, which is the voltage open circuit. This is a theoretical number. You're never really going to use it outside of your planning, and it's the max voltage it can create with no load on the solar panel. Or VMP, or the voltage maximum power point, is the voltage that your panel is going to create at its maximum power load. So when it's creating 250 watts in this case, there's a voltage there, and that's what's going to actually be what the system sees. Well, the general rule of thumb is the VOC, the higher the VOC, the better the panel, or the more power it can create, and specifically at lower lights. So when the sun is lower in the sky, you're going to create more power if your VOC is higher. So series versus parallel when it comes to solar panels is similar to the batteries. When you wire them together in series, the voltage increases and the amperage stays the same, and therefore you can use smaller gauge wiring to run that power down into your solar charge controllers. Now, when you wire them in parallel, the voltage remains the same, the amperage goes up. But the nice thing about wiring them in parallel is they become kind of independent from each other. So for example, when I put these three panels right here in series, the voltage increases. So let's say they're 35 volts. The voltage now becomes about 105 volts. And then but the amperage stays at about 8 amps. So when the sun is shaded on one panel, all three panels are affected in the overall kind of voltage and current output. But these three panels are in series, and these three panels are in series, and these two are in parallel going down to the solar charge controller. So what that means is if I shade this side, because these are in parallel, these aren't affected. This will be outputting maximum power again in good sunlight. So that's the benefit of parallel. The only trouble is when I wire this up in parallel with this side, now my overall amperage is 16 amps. So I need at least 10 gauge wiring or heavier going down to my solar charge controller. So there's a limit to how much you can really put in parallel based on the amount of wiring you want to put in here. Let's talk about batteries. I think the most important part of your boondocking, like electrical setup, is your battery bank. Having sufficient battery power is what's going to allow you to go out and dry camp without the need of a generator. So you have to think about your expectations and your goals while boondocking. Do you want a system that allows you to go fully off grid? Then you're going to need a pretty large battery bank to be sufficient for all your needs. If you want just a smaller setup and you're going to supply some extra power with a generator or something of that nature, then you can plan a system like that as well. Otherwise, the thing to think about is your nighttime usage. What are you going to need to go through the night? Do you have a residential fridge that's going to be a power hog? Or are you going to need to run an air conditioner through the night? Like, you need to set up a battery bank that's going to be at least big enough to get you from the nighttime to the morning to recharge in the morning. That's the very minimum. Daytime, not a big deal. You can run a generator anytime you want, but sometimes you can't run a generator at nighttime. Let's talk about the different types of batteries. You've got lead acid, and under that there's a few subsets. There's flooded lead acid, there's a gel lead acid battery, and then there's another one that's kind of like that. It's a AGM, absorbent glass matte battery. And then you have lithium batteries. Well, lead acid, the pros, they're cheap, they're readily available. You can get them at like any auto shop, Walmart, pretty much anywhere that sells like the large like car batteries. Those are lead acid batteries. And then they also are resistant and kind of resilient batteries. They're resistant to overcharge issues, but that's about where it stops. The cons, they are heavy. They only get about 200 to 500 cycles at the most. So that's like discharge and charge cycles. They must be mounted vertically. Okay, so they have to be upright. When, I have to sit them here, I can't lay them on their side because they have the water in there that creates a battery acid solution inside, and that'll leak out, and that'll ruin your RV, it'll ruin the battery. The biggest con to lead acid battery is sulfation. It's a process that starts to corrode and ruin the inside terminals of the battery if you take the charge less than 50% of its capacity. So a lead acid battery in theory might be a 100 amp hour battery. However, you can only use 50 amp hours of it before you start causing damage to the battery. And if you start that sulfation process and do it too often, or you let it sit below 50% for too long, you're going to start ruining the battery's ability to maintain charge and to even get a full charge. And after a while, you're going to have a battery that won't charge. The AGM batteries, everything on the AGM battery is the same as the lead acid, except for a couple, maybe three main things, and that is that because there's no loose fluid in there, and that goes for the gel batteries too, you can lay them on their side. Still not recommended to go upside down, but on their side is okay. And it maintains battery life, or the charge, better than a lead acid battery, like just a standard flooded battery, and you get some more cycles out of the battery versus a standard lead acid battery. Lithium ion batteries are your other option. There's a lot of pros to them. They're lighter than lead acid batteries. You can use 100% of their charge capacity, so there's no damage to them if you discharge them to dead. It's recommended not to do that to prolong the life of the battery, but you're not going to do any major damage or even potentially minor damage by discharging it too low. Make the cutoff 10-20% before you recharge, and you'll be totally fine. It has a lot more cycles, so discharge and recharge cycles, most of them are going to be in the 2500 range all the way up to the 5000 charge cycles range. You can charge them much faster. They will accept so much energy all at once. So if you've got a 4500 watt generator, it's going to take all 4500 watts while you're recharging the batteries. You can also mount them in any direction. You can even mount them upside down because there's no liquid inside them. So you're not going to have battery acid issues or anything of that nature. It maintains its charge a whole lot better than a lead acid battery. So if it's sitting for a while, you're going to come back to a still pretty charged battery. The high and cold temperature discharge is better, like its performance. So if it's really cold or if it's really hot, you're still going to get a lot of power out of that battery versus a lead acid battery, which starts to fail in its performance when you get to temperature extremes. And speaking of its performance, it performs so much better than a lead acid in the sense of it gives constant power until it dies. The cons, though, it's got a high initial cost. Some of the batteries are, $400 all the way up to $1,000 for a typical 12 volt, 100 amp hour battery. That's comparable to $100 for like a lead acid battery of the same capacity. So the initial cost can be outside of a lot of people's budgets. The availability of them, they're just not available as much. You can pretty much get them online. You can't just go to AutoZone and buy a lithium-ion battery. Cold weather charging is also an issue. When the internal battery temperature, not the outside ambient temperature, but the internal temperature goes below freezing, so 32 degrees Fahrenheit, 0 degrees Celsius, you cannot and should not charge a lithium-ion battery. Also, the normal discharge rate, so the amount of amps that you can draw off the battery is less than a lead acid battery during normal temperatures. But it's going to give you constant power when you're discharging those amps. But I've never run into an issue there. I've drawn 45 to 50 amps off the batteries with zero problems. And I mean, who's going to be running more than 3 ACs and then want another high power appliance as well when you're boondocking? It also requires a BMS, a battery monitoring or battery maintaining system. But that is something I'll talk about in just a minute. So which battery do you go with? Do you go with the lead acid battery or do you go with the lithium ion battery? There's a few things that's going to determine that, and that's going to be the size of your battery bank and what your budget is. Okay, your budget, I mean, if you can't afford to go buy, upwards of $2,000 to $3,000 worth of batteries in the very beginning, then you probably have to stick with some the lead acids to get yourself going. However, if you're going for a big battery bank, you need 600-700 amp hours of battery. In order to get that capacity with lead acid, you're going to need 10-12 batteries, and that's going to be a lot of weight that you're putting in your rig, and that's going to be weight limiting. So it's really kind of the trade-off of size of the battery, performance of the battery, and the cost of the battery. The better long-term one is obviously the lithium, because you're going to replace that lead acid battery multiple times before you replace your lithium ion bank. And because of that, you are actually going to probably save money with the lithium in the long run. But and then also the lithium ion it exceeds it on almost every performance capability of the battery. The battery management system that was mentioned before, it's basically a computer circuit board that monitors all the cells of the battery and keeps them within balance. Because a lithium-ion battery is not just one battery. It's a bunch of individual little cells, and those cells have to stay within balance of each other. And through a lot of discharge and recharge cycles, and specifically when you do a lot of high draw, like high amperage coming off that battery, you're going to get those cells to kind of get a little out of balance without a BMS. When a cell gets out of balance, it can be overcharged. And if you overcharge a lithium-ion battery cell, it can heat up and to the point where it causes a fire. And one cell catches on fire, then the rest start to catch on fire, and it creates this thermal runaway. The BMS eliminates that by monitoring and keeping the cells equalized voltage-wise. Also, converter. You're going to need a converter if your battery bank is a different voltage from your RV system. So my RV, all the wires throughout this, and most RVs out there, are 12 volt systems. There are some 24 volt rigs, but those are not common. So if you do anything but a 12 volt battery bank, you're going to need a DC to DC converter. So that's what this is up here. This takes my 24 volt battery bank and converts that power to 12 volt DC power so that my rig can run on the 24 volt battery bank. All right, the solar charge controllers, they take the raw power from the solar panels, and they regulate charging the batteries. The MPPT charge controllers are more expensive, but they're more efficient in how they operate and give you a little bit more range of types of panels and battery banks that you can use. The PWM charge controllers are less efficient, but far less expensive. So they're a nice, cheaper option for more budget systems. Also, they are limited in the sense that if you have a 12-volt battery bank, you have to use a 12-volt PWM, like a compatible PWM system, and you have to use the solar panels that are specifically for 12-volt battery systems. For example, they actually are outputting about 18 to 20 volts, and then as they come down through the charge controller, they're going to put a charging voltage of 14, 15 amps or whatever the case may be. You cannot use a 30 or 35 volt panel through a PWM controller for a 12 volt battery system. The MPPT, however, does regulate, and it changes the voltage of the power that's being put out of the solar charge controller. So in this case, you can utilize a solar panel that has a maximum voltage of 37 volts. And when it gets to the charge controller, it's going to change it to the voltage necessary for the battery bank. I have a 24 volt battery bank, so it's actually changing it down to probably 25, 20, or 26 volts. I don't know the exact details, but it's going to regulate that down, which means that when it does that, the amperage goes up. The amount of amps that I'm putting into the battery goes up versus the 37 volts and lower amperage coming down from the solar panel. Now, the numbers on the MPPT shows 150, 70. That means it has a maximum input voltage of 150 volts from the panels. So you can wire them up in series and parallel, however you need to, the solar panels, to create no more than 150 volts. Then it has a maximum output. Remember how it changes the voltage and therefore the amperage changes as well? It has a maximum output of 70 amps. So that's what the two numbers on the MPPT charge controllers mean. Now, then I've got a few other like fuses here that control input and then the output amperage coming in from the panels and then going out to the batteries. Right over here, I've got the negative and positive bus bars. So pretty much everything that's DC powered is all running into the bus bar here and then running straight out to the batteries, which I have in the back behind the wall here. Up top here, I've got the shunt. Okay, the shunt is a smart shunt, so it's measuring everything in and out of the battery at any given time. So it can the Bluetooth connectivity, I can see it on my phone as to kind of what's going on with the battery, the state of charge, the what I'm discharging it at the current moment, that sort of thing, or charging it. And then we get the inverters. I have a couple Multipluses that are wired together to give me basically 6,000 watts of power at any given time. The inverters, their job, these are inverter chargers, but the job of an inverter is to take DC power from your battery bank and then change it into AC power so that you can run any piece of equipment that needs alternating current inside your RV, whether that be the receptacles, a refrigerator if you've got a residential fridge, microwave, that sort of thing. All those items that would normally plug into like a wall outlet. And then also your air conditioners as well are AC powered. So inverters can also be just used to wire up like one or two different outlets inside your rig so that you just have a little bit of AC power, like you want to plug in a coffee maker or or let's say a phone charger or something like that, but you don't want to do the hassle of like wiring it into your entire AC electrical system. You can do that as well, and they have smaller inverters for that. I have mine so that it's wired up and go straight to the circuit breaker panel. So the inverters are constantly running the rig at all times. This is a charger as well. So it's taking in power from our shore power, if we're ever connected up somewhere, and can output that power to charge the batteries. And this is a 24 volt system. They have the 12 volt ones also for those that have a 12 volt battery bank. Down here, I've got a fuse block that's protecting the positive side on the battery terminal. You want to make sure that you have that protection, and I have a battery disconnect that I can shut down any power in and out of the battery, along with the Cerbo display. This is kind of the brains behind my interior whole control panel for my electrical system. You don't have to go this fancy. This is an optional piece. You can do a lot lower end, and you can even go higher end on what you want to use for state of charge displays and things like that. So this is our Cerbo GX display. It's a pretty complex system that shows a bunch of different things, not just state of charge. Kind of like the amount of power that we're pulling in off of the pole there for the grid. The AC load shows us what our RV is using at the current moment. And our battery display, of course, with the voltage and everything, along with our solar power, like what we're creating at the current moment. And then in the settings, we can control different sensors or the settings for the inverter and charger as well. The other option is a very simple display that just kind of gives you battery state of charge, like this Victron setup right here. Just tells you your voltage and or your battery percentage. Some of them even show you your amp hours left and remaining on the battery, but you're going to need some sort of state of charge display. Okay, so we need to determine our battery bank and our solar panel array size. So I've put together a series of worksheets here to calculate your total daily power usage and use that as a basis for determining those numbers. So on the front side, you got some directions for how to do all the steps. You got steps 1 through 7, which carry over into the worksheets themselves. Let's just do a couple examples here. Let's take our refrigerator. In order to get your watts, you need to multiply the volts and amps that it uses. So the refrigerator is a residential refrigerator. It's 115 volts, and it draws 1.9 amps, which gives us 218.5 watts. Time used each day. This is important to kind of figure out how many minutes or how many hours a day you use the item. A refrigerator in an RV is going to run more than in a conventional house. A conventional house, it's more insulated. You have it nice set 70 degrees or 72 degrees inside. You in an RV, your refrigerator is typically on an outside wall, less insulation. It's not going to run the 8 hours that a normal fridge runs. It's probably going to run closer to 11. I'm going to go with 12 hours just to be nice and conservative, which gives us 2,622 watt hours. This is the amount of daily power draw from your battery bank the refrigerator is going to do. Let's look at the microwave now. As you can see from the tag, it doesn't have a volts or an amps, but it already gives me 1,600 input watts for its power usage. Use the input, not the output, because it's going to be what you're drawing off of the battery and going into the microwave. If you already have the wattage on the individual appliance tag, you don't need to solve for using the volts and amps. We use the microwave for about 20 minutes a day or so that's 0.3 hours. That gives us 480 watt hours of power a day. And so section A, I've put together just a lot of the bigger appliances in your place: electric water heater, dryer, washer, that sort of thing. So this section down here is going to be for your air conditioners. You're going to notice that the ACs have quite a bit of power draw, and you may just want to use the generator for that, but you have it here just in case you want to calculate that anyways. Section B has a lot of our small appliances and electronics. And why don't we take the phone charger that I have as an example, and you can see from its tag, it's 120 volts, It draws half an amp, which gives us 600 watts of power. Well, I get about a full charge in about an hour and a half. So let's say it's plugged in and charging for 2 hours throughout the day. And that gives us 120 watt hours of power. So go ahead and use these charts to add up everything that's in your rig that you would use on a daily basis. If you don't have it, like if you don't have a sound bar for your TV, obviously skip it, move on. Over here in section C, it's kind of the random open items. If you have something that I don't have listed here, go ahead and jot it down there. So make sure you do that for every electronic in your rig. I'm going to go ahead and do that.
1 hour later.
So finished all the calculations for my rig, and we're looking at my large appliances, 6,125 watt hours being used. Your air conditioners, as you can see here, they use a lot of power. They use about 1,700 watts. And if you used it for a few hours a day, each AC is going to be running about 5,000 watt hours of power. And that's a significant battery bank storage that you would need for that. So I would just recommend using your generator to run your ACs if you need to. Here, my small appliances, all my little electronics and everything, 2,625 watt hours and 36 for just my kind of miscellaneous items there. Well, let's total that up. So 6,125, 2625, and a little 36. That gives us 8,786 total watt hours. Transfer that down to step 5. And why don't I just go ahead and get those steps out here that we can go side by side here to take a look. How's that? So as we go through here, the battery voltage. This is talking about your battery bank that you're going to create. Whether it's going to be a 12 volt, a 24 volt, even a 48 volt battery bank. 72 would be kind of overkill and not really necessary on an RV. But the idea is this is not your rig voltage. Your rig voltage is most likely 12. There's some 24 volt rigs out there, I guess. But so in this case, the most common one that a lot of people do are 12 volt. Do your research out there, and you can see the pros and cons. Even in our blog that we did on this, we talked a little bit about the pros and cons of higher battery voltages. The total amp hours, though, you divide your watt hours by your battery volts to get your total amp hours. So as you can see, your amp hours is dependent upon voltage. Watt hours, as far as capacity or power storage, is not dependent upon battery voltage. So it's really easy to do some conversions among different items using just watts or watt hours. When you start getting into amps, then you also have to start thinking about the voltage. Just one little side tip for when you do calculations. But when we're thinking about just the batteries, now we're thinking about amp hours. So we have, in this case, 8,786 divided by 12 gives us 732.2 amp hours. That means that if you're running something if you're running 100 amps, you're going to have 7.3 hours of battery to run that 100 amps. Or it kind of the way you work this is if you ran 1 amp, you would get 732 hours of usage out of that battery bank, and any other number of combinations of that. Well, I throw a 10% buffer in there. That's for if you go and you use a little bit more power one day versus another day, or you forget about a couple electronics in your thing or in your rig, or you use your TV, or you do an extra load of laundry or something a day. Like, this helps kind of buffer that. And that turns out to be 805.4, so 806 for a nice rounding number for your battery bank storage needs. Now, lead acid versus lithium ion. Lead acid. We still need 806. Sorry, that's terrible. Amp hours of battery bank. But, or for usage, a lead acid battery, you don't want to discharge less than 50% depth of discharge, because when you go lower than 50%, you're going to start a process called sulfation. You can do some research on that, but that starts to kill the battery life and the total capacity. So in order to get a battery bank big enough to handle 806 amp hours of usage, you're going to need a battery bank that is 1,612 amp hours at 12 volts. That's about 16 regular, just kind of 12 volt lead acid batteries. That's a lot of weight on your rig. Lithium ion, here's one of the benefits to lithium. You still need that same capacity number, but lithiums you can easily discharge down to 0 without doing any damage to the battery. But to extend the battery life of the battery, you want to maybe use a cutoff number of about 20%. So use a factor of, divided by 0.8, and that gives us 1,008 amp hours at 12 volts. So you can see you need less battery significantly than you would lead acid, and that's also less weight on your rig. Step 7. This is finally how much solar panels do I need? Like how many watts of solar panel? So we're going to go back to step 5, and we're going to make sure that we calculated this with 12 volts. And if you did a 24 volt system, just go ahead and recalculate this and get this number right down here in 12 volts and bring it on over. That just makes this rule of thumb a little bit easier. So whatever your amp hour is for your battery bank, or like what you use per day, in order to recharge that, just double it. And that's the minimum solar panels that you should have to help recharge that. That's thinking, all right, you're going to do 5 hours a day of real good sun. You're going to have some other sun on the front end, like from 8 to 10 in the morning. And then you're going to have some tail end of the day sun from like 4 until sunset. That's going to help recharge. So you're going to get probably 6 hours of like real good kind of decent recharge time. So that's 6 hour time. That's going to be, all this is going to be recharged in 6 hours. On the other factors is 25 degrees Celsius, which is about 77 degrees Fahrenheit, because as a panel starts to heat up more, the production goes down. So there's a lot of factors that play into how efficient a panel is, but minimum 1,612 watts to recharge 806 amp hours of power. Now, keep in mind, this number right here is minimum. In the winter, you're going to have lower sun angles versus the summer. Cloudy day, or if you're going to park in a little bit of shade, or if it's a really hot day, this production number is going to go down. So you're not going to be able to recharge this necessarily. So I would add a buffer to this number. So if it was 1612, I'd probably throw 2,000 watts on my roof if I could. But that's just my recommendation, so that on a worse day, you're still getting your minimum number to recharge. That is the basic calculation at worst case state. Remember, I had in here the washer and dryer. Are you going to do laundry every day you're boondocking? I highly doubt it. So, this might be on like the really good Sunday. Let's do a load of laundry and we'll be okay. So let's go ahead and take these numbers out. Are you really boondocking going to wash your hair, use your hair dryer and curling iron each day? I don't think so. So if you add up this right here, you're going to get a number that's about 2,800 watt hours. So let's take that 2,800 watt hours out of the equation, and let's look at what happens at to the final overall number. Let's put these side by side. And you can see subtotal A drops significantly, and subtotal B. So your overall watt hour usage is now 5,000, almost about 6,000 watt hours. So if you throw that through the equation, now you've got basically 500 total amp hours. For rounding purposes and easy math, 550 amp hours of usage per day. Well, you throw that over here, now you only need 11 batteries. Or on this, 6 to 7 lithium ion batteries at 100 amp hours each will be sufficient for you. All of this is going to bring the cost down and the weight down. Now look at your solar panel. Here you needed over 1,600 watts. Now you only need 1,100 watts to recharge. So you can see how if you cut out some big electronic appliances, you are going to significantly reduce your cost of your solar panel or just whole solar system. So if you wanted to and say, all right, well, only on like the really good weather day, I'm going to run my laundry, if you've got laundry, of course, I can get away with this smaller system right here. And then, maybe put, in this case, 1,500 watts on the roof. And on a good day, you're going to be able to run those extra large appliances. Now let's take a look at side-by-side comparison of what I actually did was a 24 volt system. So same numbers. You can pause this as much as you want to take a look at this, but same numbers going down. And right here, I did a battery volt for my bank at 24 volts. Well, it's going to cut all these numbers in half. So all the other calculations are the same going down. It's just now I need 806 amp hours, but that's at 24 volts. Okay, so in order to get 24 volts, you either need to buy a 24 volt battery that is another like an 100 amp hour battery. Or take two 12 volts and wire them together to get your 24 volts. So you're probably going to still have the same amount of battery. It's just different numbers in the calculation here as we go down. And notice your solar panel, it's the same. This is just rounding error that makes the difference here on the way down. So your solar panels are still 1,600 watts for recharging. Now let's do that same comparison when we take the larger appliances out and kind of see what happens if we go down the list here. Everything's the same down to battery voltage of 24. And the total amp hours here, it's exactly half, right? Makes sense. All the way down to 275 basically. It's half of your 12 volt system. So now you're looking at the need of a battery bank of 550 amp hours at 24 volts or 343 amp hours of lithium ion battery system. So let's take a look at, this is my scenario, kind of what I have for the rig, this, or if I wanted to look at the overall like larger bank. But what I ended up doing was lithium ion, and I have about 450 amp hours. So if you notice, the other one, remember, was 500 amp hours of battery required to run my day. However, what I ended up doing was 1,100 watts of solar. No, I went with 3,000 watts on the roof. Okay, solar panels, if you go and you can find some used panels, and they're pretty cheap. I have 250 watt panels on the roof, and they cost me $105. Now, granted, with a little bit of inflation over the last year, those panels are probably $130 now, or $150, but that's still relatively cheap in the grand scheme of things. I have 3,000 watts. Well, if my usage, if you remember and you go back, my total watt hour usage was 8,786 watts if I'm using all those big appliances. That's recharged if I have 3,000 watts in 3 hours, which means then I have 3 hours during the day of just free energy. So we've done, on a good solar day, using this and recharging my battery bank, I can go from almost dead to full charge and then run my AC for a couple hours. or I can run multiple loads of laundry and use the dryer and everything. Like I have free energy pretty much past noon or 1 o'clock in the afternoon if I've got good sun. Everything from there is full battery charge, and it's just whatever I'm using. So having a big solar array can be helpful. Having a big battery bank can be very helpful as well when you're in areas where you don't have good solar. But hopefully this helped out and giving you an idea of how everything fits together when deciding what size battery bank and what size solar array you need.